Oh, thank you. So, yeah, we're going to be talking to you about reverse engineering secure SSL APIs. Tell you exactly what that means in a second. So, first off, I'm Alejandro Caceres. I'm a CNO engineer with Lunarline and a penetration test team lead. This is Mark Haase over here. He's a senior security software engineer with Lunarline. Does some really good work. And a contributor to MITM Proxy, which you're going to hear all about today. So we'll get to that. All right, so a quick 2-minute overview of what we're going to be talking about today. HTTP APIs mainly. So they're very popular today. A lot of rich internet applications are going to use HTTP APIs. A lot of native applications compiled for Android, iOS, other mobile platforms often use these. Main reason is really they're very simple to use and also very simple to build. So for this talk, we've actually built a mobile game basically that uses an HTTP API, and we were able to do that relatively quickly just because they're from a development standpoint pretty simple and from a use standpoint also very simple. So lots of HTTP APIs need to be secured for confidentiality of the data as well as integrity of the data, and we're going to get into that a lot more later. So some of these HTTP APIs are secured with SSL, which, as you'll see, is not going to make a whole lot of sense. So SSL kind of protects against man-in-the-middle attacks, but it's not going to offer much protection from the endpoints, which we'll talk about a little later. So a little bit more about our setup here. Got a lot going on. So we have 2 endpoints. We have the API server, which is this thing right here. And we have the API client, which is going to be this thing right here. And the API is using SSL. So we see that we have an SSL tunnel there, and then we're going to have a man in the middle, which when we get into the demo, we'll show you all about. Yeah, so, sorry guys, technical difficulties. So one big theme that is going to kind of recur here is that nothing's going to be perfectly secure. So we're going to suggest a lot of potential fixes to kind of a broken API from a security standpoint, but nothing is going to be absolutely perfect. And we'll discuss exactly how to break the even more secure versions of the API. So essentially, an attacker with infinite time and resources is going to be able to break anything. The real trick here is to make it difficult enough that the attacker kind of maybe gets bored and moves on to something else, or realizes that what they're trying to hack is not altogether that interesting, and they just kind of move on. So that's kind of what we're hoping for, is to make it hard enough that attackers just move on. So basically, we're going to discuss SSL in terms of these trade-offs for API security, and we're going to present a lot of other solutions besides using SSL, which is the wrong solution.
So anyway, we're going to do just a couple quick slides, background talking about HTTP and SSL. I think a lot of this will be probably common knowledge, but we just want to make sure everyone's on the same page before we dive in to the main content of the presentation. So first of all, Alejandro mentioned that a lot of people are using HTTP APIs now. And the first thing we want to talk about is why HTTP. You can clearly use a lot of other protocols. You can even write your own binary protocol to do an API like this. So one of the reasons is that HTTP is ubiquitous. There are lots of clients, lots of servers, lots of libraries out there that make it really easy to generate, send, receive, and parse HTTP requests and responses. You can see all of the clients and servers that we have on this slide right here. Another thing that's maybe just as important is the very mature specification. HTTP has a lot of detail about it that enables building things that are very scalable. So in particular, one of the things HTTP does very well is handling multiple media types and doing content negotiation. So if your browser only deals with certain types of content and the server has multiple forms, there's actually a very mature standard for specifying which forms your browser actually wants to receive, and the server can send you the one that you can actually use versus sending you one that you wouldn't be able to use. So that's very important. And the other thing is cache coherency. HTTP has a lot of details in the standard about how caching is handled, so that if you build your API on top of HTTP, you can in fact take advantage of this built-in caching on the internet, both caching at the user's endpoint as well as proxy servers that might be caching. Roy Fielding, who wrote his dissertation on HTTP, calls this design on the scale of decades. In other words, building software that's very, very robust and scalable and highly maintainable. The other thing we want to talk about real quickly is SSL. Again, I think a lot of you probably know all this stuff, but we just want to make sure that everyone is aware of the basic idea behind SSL. It's a proprietary protocol initially that was developed by Netscape in the mid-90s. These days, there's a modern version that's actually standardized by the IETF, and that's called Transport Layer Security, TLS. In my experience, everyone just still calls this SSL. So for the rest of the presentation, we're going to call it SSL. But everything we say here applies to TLS as well. SSL typically provides two services in the way that we use it in and out every day. The first service is to authenticate the server to the client. So if you connect to Bank of America's website, SSL is what helps you determine that you're actually connecting to Bank of America and not some website that's impersonating Bank of America. The other service that it typically provides is encryption to protect confidentiality and integrity of communications. When we talk about encryption, I think even people who aren't interested in security understand that encryption is about protecting secrets, in other words, confidentiality, but it's also about protecting integrity. Good encryption means you can't modify an encrypted message in any meaningful way and affect what the person who decrypts it will receive. Now, these two services are typical. They don't have to be used this way. It is possible actually to set up SSL just for authentication and no encryption, which is kind of weird, but that actually is possible. Another thing that you could do with SSL, but I don't see this a whole lot in our work, is you can authenticate the client to the server using certificates, the same way that the server authenticates to the client. And so basically, to sum it all up, what SSL buys us are these padlocks in our browser, right? So that when we're connecting, we know that this experience is safe. We're connecting to the right place, and the information we're sending them cannot be intercepted by a man in the middle. So SSL has a trust model, and basically when you visit a website, that website will present you with a certificate. The certificate includes things like the site name, the company that owns it, the company that issued it, and their public key. The other thing that's required to use a certificate on your server is to have the private key that matches that public key. So when a web browser connects to something like google.com, you'll get a certificate. You'll use the public key to generate a challenge, and only the person that has Google's private key can properly respond to that challenge. It's cryptographically secure. The question, of course, arises, how do you detect forgeries? I could myself generate my own private key and public key. I could put in google.com and say, yeah, I'm Google, and I could make a certificate that looks just like theirs, just with different keys. And so, of course, this is a solved problem. When Google gets a certificate like this, or when any company gets a certificate, they have it signed by an issuer. So companies like VeriSign and Thought, they sign these certificates. And basically a signature means they have a certificate with its own public key and private key, and they use their private key to sign Google's certificate. So that gives you confidence that that Google certificate is actually signed, right? But of course there's kind of a recursive problem here because you've solved the certificate problem by introducing another certificate. How do you know that this VeriSign certificate is also valid? Because if that's not valid, then that fake certificate could be used to sign a fake Google certificate, and so forth and so on. And so the answer to that question is that actually when you buy a computer or when you download a browser like Firefox, it comes with a bunch of certificates that it trusts out of the box. And so, for example, VeriSign has root certificates that on your computer are already trusted. And so any time that certificate is used to sign another certificate, it transfers that trust to the certificate that they've signed. And then before we get into we've got a really elaborate demonstration. Before we get into that, I want to talk about a few real-world examples of people who have used SSL to kind of secure an API and how it didn't work. The first example is Google Reader. If you're not familiar with this, this is an RSS and Atom aggregator. So if you like to subscribe to feeds on websites, this will pull all those feeds together and present them to you. It's implemented largely as a JavaScript-heavy client-side application that runs in the browser. And actually, most of the work that's done, the aggregation and the consolidation of feeds, is done through an HTTP API, which uses SSL if you request it. And the interesting thing about this is that Google has never published an API document for this. So if you wanted to build a third-party Google Reader client, there's no Google documentation that says, well, this is how you get a feed, this is how you log in. There's none of that. And yet there are dozens of third-party clients. And so this tells us that despite using SSL, people have clearly been able to reverse engineer this entire protocol to a level of detail that's required to build a compatible client. And this isn't a great example because at least as of a couple years ago, you could also access this without SSL. So that would obviously make it a lot easier to reverse engineer. So here's a slightly better example. There's a social networking application called Path that was notorious last year for uploading people's contacts to their server. This is purely a native application. If you go to their website, they don't have any of their content on the website. You can only access this content through their compiled native applications. And of course, these applications use an HTTP API for the reasons that we talked about earlier. And this always uses SSL. Unlike Google Reader, this is never plain text. And so these old versions transferred personal information such as the address book. And since then, this has been corrected, and they've stated that, they've updated their privacy policy. But despite the fact that this API was encrypted with SSL, someone was able to reverse engineer it and see that this private information was being sent. So again, this is an example of an SSL API that doesn't protect the information from the end user. And in particular, this was a researcher named Arun Thampi who discovered this by using a technique similar to what we're going to show you today. And the third example is Apple's Game Center. And I think this is the best example, and in fact, it's what our demonstration is based on today. If you're not familiar with Game Center is similar to Xbox Live or PlayStation Network. It's a social gaming platform. You can connect with friends. When you play games, you can see what games your friends are playing, and then you can submit and view high scores, and you can see who has the all-time highest score, who has the highest score this week, who has the highest score on level 10, and all that. And this operates over HTTP API. It transfers all the scores in XML, and it always uses SSL, but this researcher, Aldo Cortese, who's actually the author of MITM Proxy, he discovered that there's no integrity checking. So you could intercept a high score request as you're playing, and you could put in your own high score, and essentially Apple's Game Center would accept that. So with his permission, I published this picture from his website based on his research. If you can see him at the top, he's me, and he has 2 billion points, 200 million points. And as you can see, I'll just let you know, he didn't actually play this well. He forged this high score and got up to the top of the all-time leaderboard. What's really interesting about this is if you look at all the scores below it, they're all the same. 2,147,480,647. That's actually the largest number you can store in a signed 32-bit integer. And so his detective work, and he doesn't know this for a fact, but his detective work indicates that these are probably jailbroken devices, and whatever game this is that he's playing stores the high score in a 32-bit signed integer. And so these people have jailbroken it, manually overwritten that value in memory, and then submitted it, and that's their way of cheating. But his way of cheating obviously is much better because he's surpassed all of them.
So now we're actually going to get into the demonstration piece of it. As Mark mentioned, we have a pretty elaborate demonstration, so bear with us. We will explain everything along the way. But basically, here's what's going on. So we've created a vulnerable API over SSL so that we can show you how to, first off, intercept an API over SSL call, decrypt that information, modify and then replay it over SSL as well. And then we're going to show you how we can protect against these kinds of attacks. So demo setup is 3 components. One is the API server, which is this thing right here, and we'll show you that in a second. If we want to plug that in. The API client, which you're going to see up on the big screen over here, right here. And then, as we know, that there's going to be an encrypted tunnel there. And we're going to show you the SSL proxy, which is going to be MITM proxy.
Run their own screen.
That's okay. just to show you guys. Can you guys read that okay? Yeah.
Probably not.
So? Well, basically all it's saying is, maybe that helps, maybe not. Basically all I'm trying to show you is we're getting GET requests and we are getting POST requests. So pretty simple API. GET requests are just going to get the 10 high scores, the 10 highest scores I should say, and the POST request is going to update those scores. So that's pretty much all I wanted to show you. We're going to switch off that annoying screen.
And just so you can see, I'm looking at the high scores now, and you can see it scrolling. So this is actually our live server here.
Just to prove that we're not lying to you for whatever reason. Okay. All right, so demonstration is going to be pretty simple to the Apple Game Center example, as Mark mentioned. API client is running a simple game. When the game finishes, it submits the high score to the API server. And the API client is then going to download a list of the high scores using a GET request from the API server. So our objective here is going to cheat, right? So we're going to try to forge the high score and make it something that is much higher than any normal person would be able to get. So. Okay. Can we show the game?
I think there's a couple more slides.
Oh, okay. So basic idea of the game is you try to hit the little green bubbles without hitting the little red bubbles. When you hit a green bubble, it starts to shard. And idea being, just hit as many green bubbles as you can without touching the red as much as possible. Okay, so once the game is done, it's going to post the score using JSON. So you see basically just two very simple fields, username and score. Pretty basic. So when we get a list of high scores, this is what the data looks like, also JSON. All right. Cool. Is that the game? Worst game ever.
Okay, so what we have here is we're mirroring the iPhone to the screen so you can see it, and then side by side we're going to try to intercept some traffic. And initially we're going to use a Mac version of Wireshark, which is called Packet Peeper, which is a horrible name, but just trust me, it's basically just like Wireshark. It looks the same. It has the same filters and everything. So if you could, Alejandro, could you first of all take a look at the high scores? So you can see a bunch of traffic as he pulls up the high scores. It's running on port 5443. One of the interesting things you can see in this packet in particular is our SSL handshake. In fact, down here you can see some plain text stuff. This is actually our SSL certificate. You can, let me see if I can zoom in here. You can see, here's my name. This is my name on the certificate. You can see Virginia, Arlington, Lunarline, lunarline.com. So this is our certificate. And then if we look at the rest of the traffic on this, what we'll see is that it's basically all gibberish. And this is because it's SSL. So if you were trying to intercept this traffic, this would not be a good way to do it. And if you were designing an API and you wanted it to be secure, you might think, well, okay, we're done. But we're actually not done because we were talking about the trade-off, trying to make it difficult enough for the attacker that he doesn't have an incentive to attack. This SSL layer really hasn't added any difficulty at all, as we're about to show. So in this window, we are running MITM Proxy. MITM Proxy is a proxy server, meaning it basically you have to configure your client to send requests to it. It will then send those requests out, and it has the ability to modify those requests on the way out, and then it catches a response on the way back and has the ability to modify the response. In particular, what makes this a unique proxy server is that it also will proxy SSL connections transparently. And the way it does that is whenever you connect to a server that it's never seen before, it creates a certificate on the fly for that domain name. And it signs it using a certificate authority that it also created the first time you ran it. And so what we've done, and if we have time at the end, we'll share this, but what we've done ahead of time is we've taken the certificate authority from MITM Proxy. If you remember that diagram we showed earlier, that was basically the root of trust. And we've installed that on the phone and told the phone to trust it. And then we set up the phone to use this laptop as a proxy. And basically those two steps, which takes a couple minutes, that's all it takes to decrypt this SSL traffic. So what we can see here is the same traffic that we were just looking at in Wireshark that was totally encrypted. And here it's totally decrypted. So we can see the headers. This is on the request. And then we can see the response. These are all the high scores. So if we modified this response, if we intercepted it and modified it, we would see different high scores in the game. But of course, what we actually want to do is to intercept the request and send our own high score to the server and try to get it to accept it. So what Alejandro is going to do is he's going to play the game real quick. And we're going to try to look at that request traffic and see if we can forge a high score. I don't think we're going to win any game design awards, but did you get in it? Yeah. What was your score? So you can see here two requests. There's a post request and a get request. If we look at the post, we can see that API that was on the slide that Alejandro was showing us, username and score, very straightforward. The API server, what it does when it gets a valid request, it just sends back the same data to you. Also, the convention of HTTP is that you would send a successful code, so we send code 200. So if we want to forge our own high score, it's actually really easy using this tool. What we can do is we can edit this request. I'll just add a few zeros and a 1. And then we can replay this. I'll hit R for replay, and you can see this little green arrow up here. Hopefully you can see that. Basically, that means MITM Proxy is replaying this request, and because this API has no security except for SSL, it is just going to accept this as if someone had just played the game and posted a ridiculously high score. Over here, we can see the response. It sent us back the same response, and it sent us this 200 code, so we know that the server has accepted it. So can you take a look at your high scores now? Yep. So you can see we've just cheated our way up to the top just like that. Maybe 5 minutes to configure the phone to do this and 30 seconds of typing. So the take home here is that SSL really doesn't protect against this kind of attack at all. Now, having said that, MITM Proxy is not for spying on other people because, like I said, we had to configure it to use this proxy server. We had to install a certificate on it. This is not like a general purpose spying tool, and we're not saying SSL is broken. What we're saying is that if you use it in this way, you're not using it correctly. So yeah. So we're going to go back to the presentation, and we're going to talk about a few countermeasures that we've put together. See you.
Yeah. All right. So essentially, we're going to start talking a little bit about what we can do about this. So as Mark mentioned, SSL can protect against man-in-the-middle attacks, but it's not going to protect against malicious users at either of the endpoints. So from what you just saw, we can intercept the API call over SSL, we can modify and replay it, and there's no confidentiality or integrity if the end user is going to end up being the attacker. So we're going to look at a couple different countermeasures. One is actually protecting confidentiality, which is going to prevent the end user from being able to view the API call. We're also going to be able to, we also want to show you how to protect integrity, which is going to prevent the end user from modifying or replaying the API call. So we're going to be using some cryptographic tools to implement these countermeasures. And a couple warnings here. Implementing your own crypto is just flat out always a bad idea. it's really easy to get things wrong when working with cryptography. So always use well-reviewed, well-vetted crypto implementations, and use the highest level functions available in your crypto library. Let the people that have thought about this extensively and coded these libraries do as much of the thinking for you as possible. Also, it'll save you time, so that's another plus. Yeah, in other words, don't try this. So preserving confidentiality, how are we going to do this? There's going to be three main approaches to that. We're going to pin API requests to a single SSL certificate, so any other certs are going to be rejected. We're also going to try symmetric encryption using AES. The client and the server are going to share the same key, and we'll show you exactly why that works in a second. Asymmetric encryption, client and server are going to use different keys. And what's not considered here is any kind of non-cryptographic obfuscation. So any kind of encodings or anything like that that can easily be decoded, not considered, and a bad idea.
For confidentiality, for protecting confidentiality, the first one is certificate pinning. The basic idea behind this, as we saw at the beginning of this presentation, a server usually authenticates itself by presenting a certificate that's signed by a trusted root, a trust relationship that was established with the manufacturer of your computer who installed that on your computer before you ever bought it, or with Mozilla, established it before you downloaded it. Instead, what we're going to do here is we're not going to trust whatever our device trusts. We're going to write our application so that it only trusts one particular certificate. Basically, we're going to short circuit the part of the library, the part of the system API that would check that chain of trust. And we're going to say, we want this one certificate and no other certificate counts. So the pros to this solution are that it's actually very simple and minimalist. It doesn't take a whole lot of code to do this. You only have to change the client. You don't even have to change the server to implement this. And there's no key distribution, so you don't have to worry about the keys falling into the wrong hands. The major con to this approach is that it's difficult to deploy a new certificate on the server because the client still trusts the old one. So if you change your server certificate, then even if it's valid and it's signed by a trusted certificate authority, your client is still pinned to the old certificate that doesn't exist anymore, and now your clients won't be able to connect. So you would have to roll out all your clients at the same time that you roll out this server change. But in practice, I think you could probably have multiple certificates or kind of like a rollout period. The second thing we're going to show you is symmetric encryption. We're going to be using AES 256, which is a block cipher. As Alejandro mentioned, the fact that it's symmetric implies that we're going to have the same key on the client and the server. The pros to this, first of all, AES is really fast, so there's not much performance overhead on this. A lot of devices actually have AES intrinsic, so you can do this in hardware. There are also lots of high-quality implementations available. So you, like we were saying, don't write your own crypto code. In particular, don't even use low-level crypto functions in a library. Use the high-level functions. Because the more that you have to assemble yourself, the greater surface area there is for making mistakes. The major cons here are that the keys can be recovered from the binary. So as we talked about, there's that trade-off between making it harder for the attacker. This makes it a little bit harder, but any attacker who has access to the binary can extract your key, and now he can do the same kind of encryption and integrity checking that we can do. And then the third solution, so the symmetric encryption API, it looks similar to the original API. We start off with the exact same request format, and then what we do is we encrypt that entire thing, spaces and indentation and brackets and everything, and we take that ciphertext, which you can see at the bottom here, and we put that into a new JSON object. So that's how the API for this works. This one's you.
Thanks, Mark. So another method we're going to talk about is using asymmetric encryption. RSA being the most popular and what we're going to use. Basically, in asymmetric encryption, one key is going to be used to encrypt, which is the private key, or I'm sorry, the public key, and then a different key is going to be used to decrypt, which is going to be the private key. So some pros to this: if the attacker gets the encryption key, he or she still doesn't have the decryption key. So in that sense, there's going to be no way that they're going to be able to modify any of that traffic for their purposes. So some cons: keys can be recovered from a binary again. So it's also much slower than AES. which in some cases might be a consideration, in many cases might not be a consideration. So essentially, this is what's going to happen. We're going to use RSA to convert the top there into ciphertext again, which is just base 64 encoded and encrypted data. So we're going to show you that. Symmetric first. Okay. All right. So I'm going to start playing the game again. All right. So as you see, we're getting a certificate error. So
yeah, so basically what's happening here is the MITM proxy is presenting its certificate, and we ahead of time have embedded the certificate of the server that we know we trust in our application. It's comparing those two and it's seeing they're not the same.
yeah.
And that's the only part we changed. All the rest of the crypto is just the same API that Haase provides.
Yeah. Cool. Now we're going to move on and show you symmetric crypto.
And also, I'd like to point out, you notice on the left side there, that didn't even send the request to the server. So there's no exposure there.
All right, start playing again.
So in this case, we can see that there's this post here to this different API, scores AES. If we look at this, just like we put on the slide, we've taken that original JSON request and we put it into a new JSON object with ciphertext. And what we'll do is we'll show you a replay attack against this. And basically, if we change even one byte of this and then try to replay it, instead of getting that 200 response code that we wanted, we're going to get a 500 response code. And if we look at the response, instead of sending us back the thing we sent it as a confirmation that it was correct, you can see here that it gives us an error. Of course, in your own applications, you don't want to send a stack trace to someone. This is just like doing it on your website. But as you can see here, when it goes to decrypt this, we're using PKCS7 padding. It sees that the padding is wrong, and it knows that it's an incorrect key, and it rejects it.
Oh, I'm terrible at this.
Okay, and then again, here's a new request for RSA. Again, you can see we've got the ciphertext here. And again, if we edit just one byte of this, and then we try to replay it, again, we'll get a 500 server error. And if we look at the response, again, there's an error decoding.
Yeah, I can. All right, so last one that we're going to show you is preserving integrity. So as Mark mentioned, some block ciphers already have built-in integrity checking. With AES, you can use CBC Mac mode for integrity checking. RSA does not have an equivalent mode. So if we want integrity only or integration with RSA, what we can do is use a cryptographic hash function. In this case, we're going to use SHA-2. So general idea is that we're going to append a secret value to the data before we compute the SHA-2 digest. We're going to hash it, and that's going to provide a unique mapping to the data. So the client's going to concatenate the following items together. It's going to concatenate username with a null byte, the score with a null byte, with the timestamp with a null byte, with a secret key. Which in our case, our secret key is literally the word secret key. So ideally, you choose a better one when you're doing this at home. So the server does the same, and then it's going to compare the hash transmitted to the hash computed. So the client can compute the correct hash without knowing the secret key. And it's going to know if any of the data has been tampered with. So a little bit about SHA-2. SHA-2 is a secure hash algorithm formulated in 2001. Hash is basically you're mapping large amounts of data into a smaller space for the output. So it makes it easier to compare. Secure hash, it's difficult to construct two inputs with the same output. Difficult, not impossible. There are hash collisions, but they're pretty rare. So some pros, it's easier to debug than an encrypted API. We ran into this when coding this. Our SHA-2 example actually works straight out of the box, whereas with our encryption examples, really easy to mess things up, as I mentioned earlier. So very easy to debug. So some cons, again, keys can be recovered from binary. So here's what's going on. So we're going to use SHA-2 to convert top data to the bottom data. Essentially, all we're doing is we are appending a timestamp, and we're creating a hash from the data as well as our secret key, which again is secret.
Can you explain the timestamp?
Oh yeah, absolutely. Sorry. Thank you. So timestamp, essentially what's going to happen here is we're going to submit a timestamp with our data. So the validity of that data is going to expire within a certain amount of time. And in our case, I believe it's 30 seconds. So essentially, if anybody wants to replay this attack, it's going to be impossible outside of 30 seconds. So it just makes it a little bit harder. All right? Yeah, that's right. We'll come back. Oh.
So you can see here, this time we've sent a different post, and as we saw in the API example,
Yeah,
as you saw in that API example, what we did is we added a timestamp and we added a digest. So we'll quickly show you what this would look like if we were to try to replay this attack. So first of all, what we'd like to do is do the same attack that we did in the first example, just maybe pad out our score a little bit, and then replay that attack. So up here you can see the replay, you can see the response is a 500 error code, and if we look at the response, it tells us hash mismatch. Basically what that means is that we sent the same hash but with different data, and without knowing that server key, we can't construct a correct hash. Okay, we're out of time, so one last thing I want to show. And also, if we were to return this to the original score, 62,000? 6,200? Try 100,000, I don't know. And we replay this attack, hopefully we got the right score there. And it checks that timestamp. And so even though we've submitted a valid hash for those 3 data fields, the timestamp is now expired. So if you're like rolling people off the leaderboards every day or something, I can't replay my high score from yesterday tomorrow and achieve a new high score. So we're out of time, but we're actually right at the end. Conclusions, we just want to point out that SSL is not designed to protect data that tells endpoints. If your user is an active attacker, then you have to take additional countermeasures in mind. And cryptography can be used to protect confidentiality and integrity of API calls, but the endpoint device can never be perfectly protected from its owner. I know, for example, the iPhone is pretty locked down unless you jailbreak it. So if you jailbreak it, I think it's pretty easy to grab the binary off, and at that point, it's just like reverse engineering any binary you've ever had. And you get into that same game that people have had for decades, well, I'll obfuscate it in my binary and I'll do weird things to try and hide it. I mean, again, it's that thing, like you can make it more and more difficult, but a determined attacker is always going to get there. Sorry, number one, I don't know. People might just like REST better than SOAP, I'm not sure. We saw in the Game Center example, Apple invented their own XML schema. That it's not SOAP, it's not really even REST.
Yeah, in that sense, I mean, that is a really good point. But in that sense, that's kind of always the problem with security, right? It is managing what assets you have with what you can provide. So if you have developers that are really solid REST API developers, essentially it's just kind of asking them to overturn the way that they usually do things that might be more efficient from a usability standpoint to something completely different that provides better security, a lot of times is not going to fly. So in that way, it might be easier to use some of the techniques that we've outlined. But that's a really good point.
So the question is, if your client side is written in JavaScript?
Yeah, essentially you don't have a binary to reverse all the information.
Yeah, exactly. It's even harder to hide information in there. I mean, I've seen plenty of people that do lots of crazy things that try to obfuscate JavaScript, but there's also an equal number of tools that will de-obfuscate it for you. So.
Yeah. Essentially, don't make games like that. Absolutely. All right, well, our time's up, but thank you guys. Really appreciate it.